Okay, so again, welcome back. So now, so far we have covered the basic of solid state, and then how to construct the shift of solid state in the plane. Okay, so now we'll come to the pseudo potential. Okay, so the pseudo potential it means it is almost potential, is it or not? But pseudo is. Okay. That means it will capture all the properties of a all electron potentials. Okay, but it will reduce the computational cost by keeping all the property of a wave function. Is it or not? So uh, before that, I will go to next. Yeah. You see, just in the QD potential, we are showing how the nuclear electron electron attraction is there. This was, is it or not? Okay. So now, because the complication arises this region. Because if you see that due to the presence of the nuclear core electrons, the wave function is highly oscillating. Okay. So now you have to, if you want to use the plane wave for that, plane wave is the not like highly oscillating sinusoidal wave. Is it or not? Okay. So now if you want to capture this guy, this core oscillation, so if you use plane wave, it will not work there. It will work there, but you have to use a very finite grid. Is it a very finite grid? So when you have to make a very finite grid of K, so you see that how many calculations you have to do, is it or not? So now what people come up with the idea, whether this, we already know the core electron does not have any contribution in your any kind of reaction, chemical reaction, is it or not? So why we are bothered about? So let us try to remove that effect. Core electron, we can generate a potential or which can give a correct basis function or basis shape for the solid state. Why? What they do that let us forget about this part. Okay, and after from here we will use a card a cutoff in the position from the nucleus, and that we will try to make a potential which can avoid the complication due to the presence of the nuclear force by nuclear field. Okay, or core electrons. Okay, so for that, what people used to do, they will develop a potential. By how they develop the potential? First, they will calculate the for a whole system. Okay, for whole system, you can develop your potential. After that, you will get some function, and then you can develop of your new potential, and you try to see that where the deviation start coming. Okay, and then after that, you cut off your potential. Okay, and then you try to use that potential as your new potential, and you use your for or calculation by considering that core electron does not participate in any chemical reaction. That is the basis of the user NSO cutoff. Okay, so now similarly, when you are doing that, so automatically it has to satisfy this. Now, question is that when you are using the cutoff, that already we know the wave function should have some property, is it not? It has some orthogonality property, some orthonormal property. So that has to be satisfied. Okay, so that is why right. So that is why we are going to use the one non-conserving potential. So have you heard about this word non-conserving potential? Who are using here quantum espresso? You are using quantum espresso. So what is the potential you are using there? Ultrasound. Ultrasound. So there is a non-conserving potential in there. Okay, no, that is a projected augmented oil. That is there, but non-conserving potential is there. You have not used it. So basically, non-conserving potential is there, and the potential same way they have developed the potential by taking care of the core electron. It does not participate. But when they are developing the potential, it has to satisfy the norm. Norm means the wave function, as I was telling you, it should satisfy the orthogonality condition and orthonormality condition. Okay, that means it should satisfy the normalization. So basically, you have to develop the potential in such a way that it should satisfy the normalization condition of the wave function. That is why that is called a non-conserving pseudo potential. Okay, and now that you are good name. First of all, using ultrasoft pseudo potential. So ultrasoft pseudo potential is basically non-conserving pseudo potential. If you use it, basically it takes longer time compared to ultrasoft pseudo potential. Why? Because the non-conserving potential, whatever the R cutoff they are using, that will be a little bit higher. Okay, so you are taking more number of K points there. In ultrasoft, what they are trying to do, they are trying to take less low cutoff so that you can take a low number of K points. But provided that you should not, what I say, no, not reject. And basically, what I'm trying to do, we are getting a business with R cutoff. So basically, from the non-conserving potential and the ultrasoft potential, that R cutoff, R energy cutoff is less in case of ultrasoft pseudo potential. So that such a way that you will not lose any accuracy. Let us say on accuracy in the your property calculation. Okay, but you will be able to preserve all the property of the non-conserving potential. So that is why it is called ultrasoft potential. Okay. So now this is I am going to tell the details about this. Who has developed this? This as a Vanderbilt has developed it. This non-conjugate is developed by this guy, and also this is the thing. Now basically most of the people, as Saswat is telling, that most of the people use in the quantum astro, so they use the ultrasoft pseudo potential as it is a less time consuming due to the use of less number of K points. Okay. So let us see that actually how it looks about the pseudo potential and the all electron potential. Okay, fine. So if you see that this is the all electron potential, fine. Okay, and this is if you the S contribution, P contribution, and D contribution. This is the thing. So and based on that, if you do the wave function, you see that this is your what I say pseudo wave function. This is your all electron function. So basically, what we are trying to avoid, we are trying to avoid these nodes. Okay, because these oscillating nodes, because this oscillating node cannot be captured by the filter. Okay, so we will take this cutoff. So here cutoff, you can see that here. Here we can use this cutoff because it is matching nicely, and the oscillation also we can use. So these things, this part we are using the wave function, provided that our core electron does not take part in the any reaction. But in case of heavy atoms, as in case of Slater and Gaussian also, we have seen if the atom is heavy, when the relativistic effect is taking place, then you have to take care of that part. So you have to add some additional point or additional function to your function as well as pseudo potential. Okay, so now, but some people are there that they said I will not go for this 4 electron concept. Okay, so we'll use full electron function. Okay, but we'll generate another function who can take care of this 4 electron oscillation. So they along with the what I say planar wave, they are adding some extra function. That extra function will able to take care of that for oscillation of the wave function, and they are generating a new function, so that you can say that I am not using any pseudo potential. I am using the all electron potential. Okay, so that is a called linearized augmented planar basis state. Okay. So these are mathematical details we are not going in. So only just you should know that this linearized augmented potential is quite good potential, which can take care of the all electron potential, and also for heavy element also it will work nicely. For that you need not to do any extra additional function, because already additional function has been integrated in the your planar basis set. Okay. So then another is that Saswat was telling, that is a projected augmented method. This has been used for the linearized function only. But to make it fast, they have used some mathematical tree. So the whatever the core oscillation function they have used, so that can convert very fast. Basically, all are mathematical trees. There is no new physics is coming. It just leads to make a convergence of the two vector first. Okay, fine. Then this is the pseudopotential library. Those who are using what I say this quantum espresso about CB2K, I think they are using this kind of potential. Okay. Anybody is using VAST here? So what you are using there potential? You are using this kind of potential. Which kind of potential you are using there? Ultrasound. Ultrasound you are using. For which system you are doing? Or what system is using?
Iron nitrate.
Achha. Iron.
Ammonia absorption.
Ammonia absorption. So it is iron is absorbing ammonia. You have replaced iron atom from the surface with the molecule. Okay. Good, nice. So you have used ultrasound potential. You have not used for projected augmented wave potential. You have not used. Only ultrasound. That's good, fine. So basically, in that people generally use for. They use this ultrasound. Earlier people used to do, but nowadays all people use only for. Okay. So fine. So this is the one of best book. Those who are I don't know whether you have read hard this book or not. You can go to his lecture also. He is doing a lot of Google, YouTube lecture. Fantastic guy. He is now around 85. Very good in solid state calculation. Okay. So now this is a very important thing. We come to the energy and forces. This is the bread and butter of the physics. Okay. They always deal with energy and forces. So now first I put in question. Earlier I put that question to Priya. So today also I put in that question. That what do you mean by total energy? Why I can write total energy in terms of potential energy and kinetic
energy? Energy includes the potential energy, kinetic energy, nuclear energy, physical energy, all other components.
So by how I can distribute the kinetic total energy in kinetic energy, potential energy? What is the basis of that? And I otherwise say when I can use this condition that kinetic energy plus potential energy. Is there any relation between kinetic energy and potential energy? Okay.
Classical mechanics.
And that we are doing as I'm saying. So why would I some reasons should be there? Isn't it?
Classical mechanics.
Exactly, you're correct. Now, why? What is the meaning of potential energy? Energy conversion is the ultimate control of that. That is fine. That is the basic of total energy conservation. These are not. But and when we can say that partition the total energy into kinetic and potential energy, is it or not? So is there first of all we should understand whether there is any relation between potential energy and kinetic energy. Is there any relation between potential energy and kinetic energy by any means equation something?
That Bernoulli equation.
No. Let us just simple think about it. Kinetic energy is half mv square. Kinetic energy is half mv square for him classical system. Potential energy, let us say, is a v of r. This is the position of r. Okay, is it or not? So now when position of r, you are telling that you are in a position, you does not have any velocity. You does not have exactly right. Exactly. So you does not have any velocity, is it or not? So that means there is no velocity component in a potential energy. That means your v is 0. Is it or not? Then only you can demark it. Nah? So one particle is always putting a constant to another term. That this term does not contain any velocity component. At that another guy, that term contains velocity component. Okay. So this is the easiest to define. So it does not contain any velocity component. So there is so you can clearly mark it. Is it or not? So this is it. So ultimately, as you are telling, total energy is conserved. So that is why things are have been partitioned between the kinetic energy and potential energy. Fine. So as I was talking about the kinetic energy, you can calculate this okay, and potential energy. This is the interaction between all the atoms in the system plus if there is any external force you are giving to the system, fine. And the force you can get from the by derivative of this potential energy. Okay, fine. So I think in the details force will about this will I think will be keeping by Professor Banerjee and Devashish. I am not going to details. So but I'll just tell that in classical dynamics, you are dealing with the force field. Is it or not? Is it or not? Force field you have heard. I think a lot of people are doing classical. They know the force field. Okay, so force field is nothing but how the atom in the system interact with each other. Is it not? That is basically interatomic interaction. Fine, nice. Okay, and there are different kind of interaction in the system. Okay, some it is a bonded, non-bonded. Okay, and that you can put in some equation. Is it or not? So it is a illustrative. It can be van der Waals, it can be bond angle dihedral. And then those in terms of if you put those interaction in terms of equation, you can write this. Okay, in terms of when it is a bond forces, when it is a forces due to the angle, due to the torsion, due to the non-bonded pairs like van der Waals, and due to the Coulombic interaction. So all you can put in the equation, but until you put some mathematical function, you cannot do anything. Yeah? Finally, your object yesterday also we have seen that the whole h psi equal to e psi, you have finally put to the mathematical equation. Then you are minimally. In this case also, when you are going to solve it, you have to put all the force, all the energy in terms of some equation so that you can do your equation of motion solution. Okay. Okay, so this is the type of the Lennard's function, and this is the those who are working with the molten salt, ionic solid, or glass. They generally use this kind of potential. So the type of potential is different because the repulsion of the atom is different compared to normal Lennard's liquids. Okay. So this is basically if you plot that this graph, this equation, you will get like this. So this is called the dispersion. This is the attraction part. This is the repulsion part, and this is the attraction minimum. Okay, now if you take the derivative of the force, potential energy, you will get the force. That's all things will be covered by Professor Banerjee. I'm not going to talk about details about that. Okay, so now this equation of motion. Equation of motion, you know that we have two kind of equation of motion. Mostly we are using one is the Newton equation of motion, and another is the Lagrangian equation of motion. Okay, because Lagrangian equation of motion, basically physicists use it. Okay, because it is easier for them to they always try to do make things complicated in terms of function. Chemistry always try to do complication in terms of reaction, and they always try to do complication in terms of mathematical function. Okay, so now in the equation of motion, basically it is nothing but the discretization of time. So you are having a differential equation, second order differential equation. So if you can discretize, you can solve your equation. Okay, so this d square x by dt square is nothing but the force. Okay, and that force you can get the derivative from the potential energy. Okay, so this you have to calculate the force from the potential energy, and then you put it here, feed here, then you can solve your equation, and then you can move with the particle from initial position to your destination. Okay, so now if you are initially at r of t, and then if you want to move, so you can move by delta t time. After delta t time, how you will move, that delta t time you will get from this solution from the equation of motion of Newton equation. Fine. So basically, how we do that? So you can do the Taylor expansion. Let us consider this in terms of v. T plus already I have shown you the Taylor expansion yesterday. So it will v of t plus delta t. So dt, and there's a second, then third. This way it will go on. Similarly for r also you can do this way. So basically we can expand both by velocity and position in terms of time. And then this f is nothing but this f guy, and this f guy will get from this form. So basically we'll get f from here. Then we'll get this. We'll put it here. And this way we'll propagate our velocity as well as our time. Very simple thing. There is no complexity at all. Okay, so now basically Bharat has given a scheme that if you want to move from initial position, but only drawback of this theory, this Bharat scheme is that you have to have the earlier position and the earlier velocity. Both you should know. Okay, so and that may be zero. But you should have an earlier position and an earlier velocity. Okay, when some initial position and velocity you should know. And now, if you, as I was telling you, if you do the Taylor series expansion, you will get this. And then if you do the another beauty of this is that they are time reversal. What do you mean by time reversal? Any idea? I think a lot of people have done the classical equation. I think monoclonal. Have you ever heard of the time reversible? No. Time reversible means if I have given a positive time and delta time, if I have gone advance, same time if I put in my equation, I will go back to my earlier position. If you satisfy this is called time reversal. You have not heard this. So that is the difference between classical and quantum, no? Is it or not? So this is time reversible. Fine. So now you see that Verlet algorithm, what is there? This R t plus delta t. So you have to know the position, the present time. You have to know the position in the past time, and then the force in the present time. Okay. So this is okay. Present time I can know where I am. I know my force where it is now, but I have to have my data about my past position also. Okay, so this is the one of the drawback in simple Verlet algorithm, but that also you can calculate because you can store that when you are since the time reversibility is there, so you can take care of the concept of time reversibility, and then from the time reversibility you can put here. So problem is not there because we are applying the time reversible property of the system and can solve it. Fine. So last line is not coming. Rule is not. Here actually I have used that if you want, here what we have done, we have this and this we have added, basically we have added this equation. Good. So here we have added and then we have got, now if you subtract these two from here to here, you will get this equation. Okay, but sometimes we need velocity. Is it or not? Always in position we cannot do everything. Is it or not? Sometimes we need velocity. So velocity scheme was not there in the Verlet. So if you want to calculate the velocity from the Verlet scheme, so basically it is nothing but that in your advanced position, from your position to your advanced position, you take the position and as well as your previous position. And if you divide by 2 into delta t, my total time you have moved, and then you will get your position. Okay, but here also you see that you need the old history of your position. Okay, and that whole history you can use this time reversible concept and you can get it. So this is the whole picture of Verlet. You can do that, and when you know the R and B, you can calculate any kind of property using the statistical theory. But Professor Tamal Banerjee is telling that a detailed lecture is there, so I think he is going to present that. Okay, so now to avoid that problem, that I want position and velocity simultaneously. So that is why they have come with the velocity Verlet algorithm. So then this is the position we have already seen, and this has been redefined how to calculate the velocity. The time history, position history is not required. So here, there you need position velocity at present time and force at present time as well as force at future time, so that you can easily calculate. Okay, so that is the key. So if you want to how it has been evaluated, how it has been come, you can take it as a homework and you can check at your home and you can do that. It is very simple, just some manipulation. Okay, fine. Okay, so now when we are doing the MD simulation, always we talk about the how long we should do the simulation. Is it or not? Fine. So that also you can try. It's a trial and error method. Either you have to go to some literature for similar system people have done or not, and they have reported some properties or not. Is it or not? And then from there you can check what I am going to do. It's similar, so that kind of box. I'm not going to talk about anything about engine builds here. Because the experts are there, they will talk about I think tomorrow. So I'm not going touching anything there. Okay. Just why I am telling about that, because I need those concepts in CPMD and UMD. Okay. So that is why I am telling that part. Okay. So this is one of the I think Bible of molecular simulation. It is called Allen and Tinsley, and this is the Frankel Smith. Okay. So those who are doing classical force field, they should definitely do it. Okay, otherwise their learning will be incomplete. Okay, so now I will talk about that thermostat. Okay, so basically thermostat means, so when you are doing a simulation, okay, so you have given some initial position and initial velocity, is it or not? And then you are propagating the system. So now you should know that it is conserving the total energy of the system. No? So how to check that? No? Is it or not? So you will use some kind of ensemble, NV, NVD, NPT. The details I'm not going to talk about it. So now, what is the role of this thermostat to your simulation? Means what are the systems you are studying? So suppose your system you are running. Okay, so now you can calculate the what I say, this temperature. Suppose you have given a 300 degree temperature, 300 degree K to run your simulation. Fine. And now you can calculate the instantaneous temperature using this equivalence theorem. Yesterday I discussed that if degree of freedom square is basically you can calculate this 3/2 and then half. So this from there you can put half kT and then you will get the instantaneous temperature with respect to your actual temperature of the system. Okay. So now you will always see if you plot the temperature T of T versus time, will be there is a fluctuation. Okay. So now you should not have that fluctuation. So you saw how you can do. You have to this instantaneous temperature. If you take average, and you will get your actual temperature, what or actual temperature or your desired temperature. Okay. So you want to suppose instead of 300, you want to run it at 350 K. Okay, so it's 350 K, whether it is really having a 350 K or 320 K. So that you have to check. Okay, so that you can check by taking the average of the instantaneous temperature and you will get the temperature of that ensemble. Okay. I am assuming that you know what is the ensemble. Okay, fine. I am not going to details about that. Okay, so now how you can control the velocity and temperature? So there are different ways you can control the temperature. So you can just biased and say and can tell that my system, if I am running at 350 K, it will be running at 350 K. There is no other way it can be disturbed. So that is one way you can control the temperature. So that is people don't follow in general. Then proportional control. Suppose as I have shown you, the temperature you can calculate from the velocity, that r double dot square. That is nothing but velocity. Okay, so you know the velocity, and I can scale the velocity. Okay, so because I know if I know my desired is TD, or my value is coming TT, and then I can use some constant so that T and TD and TD should be constant by some carrying value, is it or not? So that you can do that is called proportional control. Okay, another is the integral control. Now I will play with the Hamiltonian. Okay, my Hamiltonian is there, so I am telling you, Baba, I am adding extra term. So if anything is coming from anything, so that extra term will take care of that, whether it is a temperature, whether it is a pressure, or it is a electric field, whatever is there, that extra term will take care. So that is called integral control. Or another is the stochastic control. That is called, if it is basically if there is a system is there, if there is a friction is there, okay, or if there is a random force is there. So that random force or friction is not involved in those earlier three. So that is a new term. So for that I have to use some extra parameter to control the friction as well as to control the random forces. Okay, so this four way I can control my thermostat. Okay. So this is as I was telling, you can do the velocity rescaling, just what I have told that you can put one constant parameter which can scale your desired, this is your desired temperature, it is your instant temperature, and you can do the scaling. I am not going to details, all will be I think by Banerjee. Okay. Then this is the thermostat. Another two types is there. This is called weak coupling and another extended system coupling. As I was talking about that in the third point, that integrated system. So that comes under this extended system coupling by Nuzet-Hobart temperature coupling. Anybody has heard about Nuzet-Hobart thermostat? So you have done. So you know that. Is it or not? So when you are using it, in which ensemble you are using it? NVD. Why so? So, but when you are calculating diffusion, it is always better to calculate in NV ensemble, isn't it? NV, because when the energy should be constant, isn't it? But any kind of transfer property should be always calculated in the NV ensemble. Okay, fine. So here also this one coupling. This is a weak coupling thermostat. This is called Bell temperature coupling. So the same principle. I am not going to the details. that the expression is there. Only that idea is that whatever your desired temperature is there, at the desired temperature, how to maintain. So for that, people have come up with different mathematical expression, and always the role is that how to make it fast and more accurate. So that is the funda. That is why different kind of thermostat have come. Okay, so then there is a Nujahwar that he has used your good name, please. Ron. Rontu. It's a good name. So Rontu has used this Nujahwar extended thermostat. So there is a two different terms are there, and that you have to control those terms, and you can finally you can see that there is always this T0 and T. So you have to have your desired temperature. So they have some mathematical expression is there, and they have used it, and some coupling parameter always there because you are using some external bar with your engine belt. So always there is a coupling, and so that mathematical expression we are not going to details because we have to go to a more complicated system. So, and then as you are talking about that, if you are a friction is there, stochastic by random force is there. For that, you have to use some different kind of thermostat that is called Langevin thermostat. So this is basically tau is nothing but the friction, W is nothing but the random force. Okay, so you have to take care for it. So as per your system, what you are going to study, what property you are going to study, accordingly you have to use your thermostat. Okay, I am not going to speak anything about barostat, so that will be taken care by other people. So this is the paper article as well as book you can read for understanding those more fundamental about the thermostat. Now I will come here. Okay, so Rantu, you have used classical possibly. Is it or not? So how they no, you need not to do the. You have used hybrid or you have not used?
Classical.
No, I am asking about classical only. So, so this is just for simply I have generated data. Rontu will tell me what it's telling. Actually, Rontu, what is it basically? Here it is energy, here it is a distance, coordinates. So what I have generated here is actually potential energy, isn't it? Potential energy profile. Hey, it is not a potential surface, it is a profile. Surface means you have two coordinates. Here is not a two coordinates. So when 2 degree of freedom will be there, then we will get a potential surface. Since here my degree of coordinate is only 1. Yeah, so it is a potential energy profile, as you have seen the Lagrange potential. Okay. So this is the Lagrange type of profile. Okay. What I have done basically here, I have taken a one metal ion, and this is definitely one water molecule, and I have tried to vary that from the distance, and then have calculated total energy. This is a purely quantum calculation I have done. Okay, and I have started by keeping constant the distance, and then I have plotted the total energy. You can do anytime you have done this kind of plot, anytime in your research. Very good boy. Actually, you should always do this kind of. Then you will get a feeling when you are doing the simulation. Those who are doing the classical analysis. You see the potential profile. So if you go on this, so what I have done, I have done the keeping the constant, and then I have done a total energy calculation. This is what you call single point energy calculation. And then if you do this after a certain time, you see that it is getting the repulsion is because electron cloud is coming together, so they are doing the repulsion. And from there, whatever you are getting, that I think if you fit in your Lagrange potential, there you'll get your sigma value there. And from the energy, you'll get your external value. Okay. So this is the way the people generate your classical force field. Is it or not? So now the limitation is there because you are taking a single system. Is it or not? Single molecule, and then you are trying to calculate a bulk system, a condensate system. Okay. So that means you are avoiding a lot of things here. Is it or not? That we have the Van der Waals type of interaction, any other kind of interaction, polarization type of interaction you are avoiding. In your portfolio, you are not taking care of that. Okay, fine. So this basically we are using one method where basically we are not taking all the information of the system we are studying. So and then we are calculating and trying to match with the experiment, and we are trying to get a very good excellent result, but by using an approximated system. Okay, fine. So I say Suntu is telling, Suntu is telling that he has used NVT for diffusion, but diffusion calculation NVT is a little bit error. But I also use NVT for diffusion. Don't worry. Okay. So now this is the potential analysis. So basically that if you, as I've already shown you, the force you can use for solving this Newton equation of motion. Okay, fine. So now I'll come to the BOMD and CTM. Okay, so now I will not use any parameter force field. Previous slide I have shown I am going to use sigma. Or other than in the NJ potential, you have seen there is a sigma and epsilon. Epsilon is taking the interaction, and sigma is taking your the distance position. Okay. So now the beauty of this method, what I'm going to tell you now, I will not use any parameter here. So I will go from the first principle. So already yesterday we have done the DFT calculation. There we have not used any parameter. We are doing the first principle. Okay. That we have tried to develop a true wave function. And the true wave function, we have tried to calculate the exact ground state energy of the system. Okay, so there is no so there is no approximation if we can consider in a density functional theory. Okay, so now from the density functional theory, we will get a total energy. So there is no approximation. Let us assume that, and now I will use that energy derivative as a math force. Okay, so I will avoid by taking any kind of parameter. So that is it not taking care of the polarization or other things, manual parameter. Okay, fine. So basically, as I told you that we can use either Newton equation of motion or we can use the Lagrangian equation of motion. Both are basically same. Okay, and they will give the same result. Only the representation is different because mostly Lagrangian is developed by physicists and CPMD and BMD has been developed by physicists. So that is why they always go with the Lagrangian type equation of motion. Okay. Also, derivation is very easier in Lagrangian equation of motion. So now let us see what is happening here. So yesterday we have seen this thing that if you are having you will get a ground state energy if your density is a true density. Is it or not? Yesterday we have discussed that part. So basically, then that thing we are putting here. So this is my equation of motion. Okay. So now this is similar to Newton equation of motion. You see this is my force. If you take this guy there, so basically the same thing is there. Is it or not? Okay, fine. Agree to me or not? Huh? Is it or not? Same thing. Okay. So only that energy what I am getting yesterday what I was showing, same energy I am using there now. And that energy I am using directly. Okay. I will take the derivative. Now I will see that whether I can take the derivative or directly or not, that I will come later. Then the question you should ask me that whether we can take the direct derivative of the energy in this equation of motion or not. That will come. Now that is the one kind of this is called Born-Oppenheimer dynamics. And then another is the Karp-Pellinger dynamics. So Karp-Pellinger, what here Born-Oppenheimer, what is telling that my equation of motion, I will optimize my structure. Okay. In that optimized structure, I will get the total energy. In the total energy, I will get the derivative of this guy, and then I will move my nucleus. Fine. So there is no approximation here. Absolutely good. Is it or not? I have the total energy, and I will take the derivative. Under the total energy, I will propagate my nucleus using the equation of motion, Newton equation of motion. So my system will now behave classically. There is no ambiguity in that. Now, here what is happening in every step, I am doing first structural relaxation, and the relaxed structure, I am propagating the Newton equation of motion to get the dynamic. Okay. So see, Karp-Pellinger came with the idea that why I should do every time this optimization. Why I should do every time optimization? Because optimization takes a huge time. Those who are doing this this kind of simulation. Okay. Now they come with that I will propagate my orbital also. Along with, so nucleus is moving, so orbital is there, they also should move with that. But my point, what BMD was doing that my orbital has been relaxed then as a whole I am moving. So my orbital is relaxed, I am moving. But what CPM is telling that okay, I will do only one my orbital relaxation, then I am propagating. But every time I will not. Every time I will not do. So now my motion is fast. You see, what I am doing? I am here. I am coming here. I am doing structural relaxation. I am moving again. But what CPM is telling that I am doing first relaxation, then I am not doing again my structural relaxation. So I am moving fast now. Is it or not? So that is the fund CPM is giving. Okay. So but that for that they have to pay money. That they have given a 56 electron mass here. I will come later why it is coming. Okay. So then if you give this way, and that same way you are calculating the density, there is no issue in calculating this energy. But they, here also we are using here also. So later on I'll show you that both are same basically. If you make mu 0, automatically you will see that both are same. Okay. It should be same, is it or not? So now question is that when you are moving, basically we are not moving electron. This is a as per convention, people used to say it is electronic velocity. We are not moving electron there. Basically we cannot move electron. We are especially moving orbital. Okay, we are moving orbital. Fine. So now when you are moving orbital, you have to see that they are satisfying the condition of wave function, normalization and orthogonality as well as orthogonalization. So I have to put a constraint that when I'm moving that orbital with the fixed electron, they should not deviate from the wave function property. So for that we are putting a constraint in the CPMD. Okay, when they are moving, they should maintain the orthogonality as a orthogonality of the wave function. So a constraint we have put here. Okay, mathematically it is looking difficult, but it's simple. Okay, so this is the picture I have shown you. Is the BMD picture, one is the CPMD picture, and both we can use for dynamics using ab initio, means we will not use any parameter, though we are using in the classical MD. Fine, up to that. Okay, so now I will just tell you about what does it means. Whatever I have told, that I have written only. The electrons stay in the adiabatic ground state at any instant time. So that means adiabatic means those who know thermodynamics, there will be no exchange between the two different states. Is it or not? Okay, so that is called adiabatic condition, ground state. Then what I have written, the nuclei move on the ground state, Bornheim. Already we have discussed about the Bornheim circle. So nucleus should always be in the Bornheim circle. It should not divide from the Bornheim circle. Okay, that means the nucleus electron, they should maintain their relation. Okay, when they are in the when we are not doing the dynamics. Okay, that same relation they should maintain. Fine. And then that already, what is the condition that I have given? That the condition is that if those who have studied the excited state, that if you want to, suppose you are in the ground state, now there is an orbital, always there is a room is there. Okay, you can stay there also. But for that, you have to satisfy that when I am moving from one position to one position, my energy should not be such that instead of moving this direction, I am going there, I am moving there. So if my energy is high, so I will not move there, I will occupy that higher order. So that condition you have to check. So you should that energy should not be very high, so that you are deviating from the Born surface. Fine. And then I already have told, I have shown you the minimization at required at each every simulation. Okay, because every time you have to minimize and you have to I have shown you so that it is quite slow. Fine. And then life is same as we are doing. This is the same thing like you have made a Newton equation of motion. Only that the force we are getting, that is direct derivative of the energy what we are getting from the density constant theory. Okay, fine. Now whether we can do this or not, that you have to check it now, that whether we can take a direct derivative of a Hamiltonian. Okay, so that also people have solved. Very long ago people have solved it. That is basically by Hellman-Feynman theorem. Okay, so I will show that. What is that Hellman-Feynman? That is three-line solution. But if you do the exact derivation, it is I think more than 100 pages. Exact derivation. But the way I will tell you, it is three-line only. Okay, you see what that guy has done. So this is a force. Now my question is that whether I can take direct derivative of the Hamiltonian. Is it or not? Okay, so that he has proven that is okay. You can take that. So what they have used? So you have taken the derivative of this. So first I have taken the derivative of this guy. I can take partial derivative. I can always do those who know the partial derivative. I can take the derivative of first side. Then I have taken the derivative of the last second side. So I have taken all my three variables are there. I have taken the three variables of that. Now here I am using the brilliant guy of Dirac model. Dirac, you know that Dirac. Dirac, have you noticed that you can write this h of psi equal to e psi. So there, here I am using that notation here, and then I am this part is absolutely fine, no issue with me because I want this only. I want this only. H is nothing but the energy. So I want a derivative of that, is it or not? So I want that. So now using this relation, I have come with this. E dsi of dRSR and d of dSi. And then if you convince it is nothing but minus 2 E of dSi, and dCi by dRi is basically 0. Why? To maintain the orthonormality and orthogonality. I am not going into the detail, but to maintain the orthogonality and orthogonality, that term is 0. So basically, what I was looking for, that I should have a force which I can get directly from my Hamiltonian. I have what? Okay, so my life is now absolutely easy. Is it or not? So nobody can question me whether I can take direct derivative of the Hamiltonian or not, because we can do that. Okay. So now we have proven that we can do ab initio simulation from the direct derivative of the Hamiltonian. So now whatever we have got, so now total energy we can dAUI. So total energy Hamiltonian was there. So Hamiltonian already consists of a nuclear part as well as electron part. So that only I have done here the suitable potential to ion cores. And another is the interaction of the ions of the nuclear interaction and the ion nuclear interaction. So that part is I have taken. So if you do the minimization, yesterday I have shown the d by dx should be 0. So that is so. So now we are in a position we can move as for the force calculated directly from the total energy using the classical equation of motion, equation of motion. And we are considering the size of the nucleus is quite large compared to the electron, so I can consider it as a moving as a classical particle. So there is no issue at all. But my here is that my force I am getting, it is totally abelian. There is no parameterization in that. Okay, fine. Okay, so as I was telling that really basically CPMD what they are doing basically is nothing but weird. So I will show that how much time I'm having. Right. Okay, fine. So basically, you see that in CPMD, let us consider that total. If you see that expression, let's come back. This expression, this is only extra compared to this. Is it or not? You just see. If you make it 0, it will be like this. Is it or not? So I can write CPMD equation that in the total energy in bound autonomous surface plus this extra term added by this Karp-Marine law. Okay, so basically this is nothing but the electronic energy. Okay, fine, the kinetic energy of the electron. Rather, I will say the orbital. Okay, so now it should satisfy a condition. Just of now, I cannot give any value to this T of L. It should satisfy some condition. What is the condition? That if you're already that just you have added some constant, to the bond of an total energy. But whether you can add any amount to that, so you have to see that. So that is why they are telling that T of this guy should be very, very less than total energy in the bond of energy. If you are having this energy is high, so you will broke the bond of surface. So that means your system will not be in the bond of surface. You will be away from the bond of surface. So once you are away from the bond of surface, what you are doing the calculation, everything is wrong. Okay, so you have to maintain that. So how to maintain that? So basically, this is called, this is famous. It is called addiability. To maintain the addiability, there should be no exchange of energy. If electron energy of your orbital is going up, so there will be exchange of the energy with the nuclear. So then automatically you are not following the a bond of atomic surface, because there should be no exchange between energy of the orbital and the nucleus. Why? Already we have assumed in the Born-Haber approximation that they are independent. Is it right? So now you are trying, if you give an energy from this guy to this guy, so that means you are not following, you are actually deriving from the Born-Haber surface. So everything is gone. Is it or not? So now you have all physics is lost. Okay, so you have to maintain that. So that is why this cross is there. The electrons have to automatically follow the nucleus. So now, if there is an energy transfer from the nucleus, I am telling you, the electronic temperature increases and the system is the BO surface, and then this is not valid. So you have to always see that you are actually basically maintaining the condition of the BO. Okay, Born-Haber approximation. Okay, so those who are interested, very nice paper, physical regulator. It should be later. I don't know how it has been leave. Okay, it should be later. Okay, so you can go through that later. It is nicely presented by CPM. Okay, so now CPMD basically that what I have discussed, that only I have written here, the coupling between nuclear time evolution. Fine. Okay, all point I have written. So now I have got a two equation. Fine. One is for my nucleus, another is my, but they will move together. In earlier BMD, what was happening? I am first doing the electron structure illustration, and after that electron structure illustration in the structure, the total energy, using the total energy, I was moving my nucleus. But here both guys will move together, the nucleus and orbital, by maintaining the adiabaticity. Okay, so that means your life in school now, because you will save a lot of time, is it? Let us see, is it or not? Okay, fine. So let us see. Is the time is more. So basically, now let us just can represent in terms of what I say frequency. So if nuclear frequency is going in this direction, your electronic frequency should go the direction. They should not follow the similar kind of frequency. If they are following the similar frequency, there is a chance of getting trapped both together. But we have to avoid they should not come together. Okay, never. So basically that means what are the frequency will be there, that is defined by those who know I have discussed already, E homolumo gap but band gap. Either if it is a condensed system, it will be band gap. If it is an isolated system, it will be homolumo. Okay, so they are basically identical. Okay, so now that WE is defined in this way, so my mu, the WE, whatever is there, if that is high, this side, so I can maintain always the difference between the nucleus, and so there is a less chance of getting exchange of energy between electron and nucleus. Okay, so my objective should be W should be high. How I can make W should be high? The mu should be very low. Is it or not? Now, how much low I can maintain the mu? So that we have to check. So that only I have written that if you can decrease the mu, so that your W minimum will increase. So you will get a better energy. So there will be no exchange between energy of electron and neutron. Okay, but there is a price I have to pay. If I am going to make mu very small, my delta T will be also very small. Okay, delta T is, but delta T means the time increment. So my time increment also should be high, is it or not? Otherwise, I will not able to move very fast, is it or not? I will be in the my initial zone only, is it or not? So I will not able to maintain algorithm hypothesis. I think Banerjee may tell about what is algorithm hypothesis. Okay, so algorithm hypothesis is nothing but basically ensemble average and time average. So how we can maintain that can reproduce the value of time ensemble average by taking time average. Okay, so that Banerjee may tell. Okay, so now my delta T it will be very less if I increase this mu. Okay, so I have to. So there is a if I use reduce mu, I will get a better adiabaticity. But if I increase mu, this will get affected. So what I will do? Let us see. So now I am taking that BOMD and CPMD is basically identical. BO and CPMD basically identical. So people have plotted that force that calculated for this system. I have taken from a silica crystal. They have taken, and if you see that both are force almost same. Okay, CP is a continuous line and BO is a point, and then that people have taken a difference between force of CP and BO, and they have plotted. If you see that they are within, they are oscillating about 0. So from there you can say that both are basically identical if you are able to maintain the additivity of the quaternion organization. Okay, fine. Now basically this some value people have reported that if your energy gap that I was talking about, that W which is related to the frequency, if is around gap is 1 electron volt, then your W max will be around this centimeter inverse. And that time people have done the study and they have come with that you can keep the value around 400 to 800 atomic unit, and your delta T is actually around 0.1 to 0.2 femtosecond. Rantu, how much femtosecond you are using in your classical electricity? 2 femtosecond. So here this guy is using 0.1. So that means this guy is in disadvantageous position, is it or not?
No, sir. Tell you how much smaller step it take, that much the accurate will be the calculation. For larger step, it will be the less accurate.
So it has to be accurate.
And more accurate.
Accurate. Now, but you are so in your if you are taking 2, this guy is 0.1. So that means what is the ratio? 0.1 and 2. 20 times. So this guy is 20 times slow.
Yeah, sir. Compression factor.
Isn't it not? So 20 times slow. So if you are doing 20 nanoseconds, this guy will do at the time 1 nanosecond. Is it like that? No, just not like that. This is much more slower. I'm not talking about that. So basically, then is there another attention is that if it's a metal where the gap is 0, I have shown you that if gap is 0, is it or not that frequency is related to the 1 by mu, right? That gap is 0 means it is gone. So you can use for metal this system you cannot use for that. Okay, so there will be automatically already in metal electrons are free electron moving. Na? So that problem is arise. So you have to define some way how to handle that. Okay, so that is the point. So basically, as I have already told that T of nuclear kinetic energy of nucleus should be much higher compared to this, so that only you can maintain the additivity. Okay, the temperature of the electron it is better to keep constant because if it is high, it is a chance of going up excited state. So that means you are losing your BO. Okay, and total energy is constant. It is obviously, is it or not? It should not be high. So this is just one surface. If you want to do the calculation, CPMD it looks like this. This is just a point. And now this is the things that delta T I was talking about. 0.1 to 0.2. The advantage of BOMD is that you can take care of this file. That's what Rantu is using 2 femtosecond. You can use 2 femtosecond here also. So basically, the advantage of BOMD is that you can propagate with the larger time thing. But only that disadvantage that every time you have to do the nuclear. So you have to have a very powerful computer. If you have a very powerful computer, so BOMD is it is better than CPMD. Because in CPMD you have to play with every system that mu. Whether mu will not be, suppose if you are doing water, whatever the mu will be water. If you do for methanol, it will not be the same. So every time you have to optimize that value. So that is the disadvantage of mu. But CPMD advantage is that you can go very fast compared to here. Okay, so this is another. I have borrowed all the idea what I have taught you today from this guy. You've heard. This is what we got from the very beginning on this CPMD. Okay. And this is basically I am using in my BSc BOMD, not CPMD. Everyone has started CPMD. We have trying to understand that how CPMD works. So right now we have started. So BOMD, because if you want to run BOMD, because I have used one. As I have told, since we are in BSc, we are using this nuclear fuel. The thorium is one of the nuclear fuel. So the thorium, how we react in water molecule, simulation in BOMD. For that, is the input is there. One inter file. Those who are using BAS, I think somebody else is using that. So you know that inter file is there, is it or not? Postcard file is there. This is the position, is it or not? And then this is this POA. You have used ultrasoft. I have used POA. That is it. Okay, and this is we have run it, and then I'll show you some result. This is basically all the output. Your good name? Diksha. Diksha have got this data na there. Key points, incar postcard. Then if you run this XZ card to generate OSDI card, you get a chart from there. Is it or not? So all card sort of thing, DOS card, all sort of things will be generated. Fine. Now that I was talking about that in case of classical MD, you just check whether you have reached the equilibration or not. So you have to take the estimate time, how temperature profile be. So here also we have just plotted a temperature. This is a demo I have taken from Raymond. Raymond have just published a paper in lithium chloride in water. So this you see that there is a average is quite good. So that means your system is a equilibrium system. Okay, and then this why we have calculated for thorium. This is for thorium. This is for plutonium, and then this was for thorium. And you see that why I wanted to show this result. Basically, that we have done it is not for that. That we want to show that you see number of processor I have used 128. I have used 77 hours. I can go only 5 picoseconds. Yeah, it is okay for you, acceptable. They go, it is not acceptable. Now you are see that we have used number of processor 80. I have gone only 10 picoseconds. I have run 144 hours. Okay, Professor Banerjee also, I don't know whether you will accept it or not. I have used 160 processor. Plutonium, it is heavy element. Okay, you just see, I have run 8 days. It has gone only 0.6 picoseconds. So life is so slow, is it or not? But the life is so accurate also. Okay, so now you have to trade off between the slowness and accuracy. Is it or not? So you want to go with accuracy or you want to go with slow? Okay, and then this is another system we have used the number of water molecules have increased here. 256 water molecule we have there. This we have used here 400 processor. Okay, all are supercomputer. Just imagine 400 processor, and we are able to run 19 days and only 8 POC. Okay, and this is another big system we have run. That is, we have used 480 processor. We have used 512 water molecule, and you see 10 days we have run. We have gone only 6.6. Okay, so you have to either use your time or you have to increase the. Now that is why I was telling a strategy when you are running the competition. Always you check the linear scaling. Linear scaling in the sense that how much node I put in. Okay, so small system check where bigger system and people system. You plot it with respect to time and your the desired output, and then check that here is really linear scaling or not. If it is not really linear scale, you try to develop your own parallel code, and that you can achieve the linearization. So then 0.6, though Rontu is not happy with 0.6, so that I can make it 60 picosecond, then Rontu may be happy with that. Is it or not? So that we should do. That is why we should always do understand that how any software works actually. And you should try to understand that. Then only you can develop some advanced thing. Otherwise, publication is very easy. There is nothing difficult is there. But until you contribute something that which other people also can use, is it not? So your another thing should be there. I should contribute not only in article publication. I should contribute some advancement of this that thing what I am doing. Okay, fine. So all those things is a very good collection of the article. Those who want to interest at CPMD or BMD, they can do this. And again, the acknowledgement, fine. And then again, I always like Abdul Kalam quote. People say that. Sometimes होता ना अरे मैं fail हो गया. Basically fail हो गया. You have not failed basically. Basically you have not put any effort only. If you put any effort, you can never fail. Is it not? So I always like Abdul Kalam. So that is it. So any question, you can tell me. I will happy to. Any question? Yes, no, basically also. Nowadays a lot of function happen. But actually, DFT people are in the superconductivity, then actually they use some different concept that is called T emerge. What the name T emerge? That's called diamagnetization. T emerge. For that, you have to using the Eigen spin system. So using that concept, the superconductivity it will be similar. Is it not? So then when there will be no electronic interaction. So then for that, but it is equivalent. Equivalent died. You have to construct a Hamiltonian and different way. By equivalent time. Equivalent use, not time. Equivalent use. Absolutely no. Yes, please.
Here comes from the physical significance.
Wave function का physical significance इसलिए कहता है कि psi whatever psi is there. You cannot differentiate in terms of any physical observable quantity. You understand what I mean? Physical observable quantities. मतलब you always our mind or brain inside that if you can see something, we can easily conceive that. Psi is a mathematical constant we don't have at that. But in case of probability density, you can have a probability density, you get density. So you can easily correlate that this is one kind of density. Okay, so that is why called psi square having a physical significance, but psi does not have any physical significance. Because you cannot correlate with any physical observable quantity. Because if you know the probability density, you can easily correlate whatever I have discussed with the electron density. So that is our other, there is no other. So anything, any question? Otherwise, later on, if you want to start CPMD, BMD in your life, anytime, in your life, always the force of energy is there. We have done. Now, whatever that we have not done, we cannot teach you. But whatever we have learned, that definitely we can do that. Okay. You can always come to BSc. Okay, but I didn't know we are saying some procedures to come, so you can mail Demon also, mail me also. So there is a procedure to come BSc. BSc, you can stay there 3 months, 6 months, 1 year, but BSc will never pay any amount to you. The BSc does not have that kind of architecture. I would say matter is accommodation BSc sometimes provide. If you're going to work departmental work it's related to the BSc. So accommodation may be free of course, but no extra stipend. Always you are welcome to BSc. Pick up any kind of what you want. But that's my end. Another.
Any other questions? Only thing you require a lot of computational resources.
That is I told you. Since we have the resources, right now we have reached eight peta. Now it is being made 10 peta. I think the record in India. That India has a 10 peta block, but that we are using for now strategic purpose. That we are not using for. BSc we are having a 2.86 peta. We are trying to make it around 6 peta. I think by next year we'll be able to make.
But then how will they run their programs of this PMD or CPM? Because for them,
So if they are going to make a dynamic simulation of dynamic system, they want to run. So CPMD basically for a time phenomena. So it's very difficult to run in a normal workstation or normal server. Because you can run if you take a let us say 16 watt of molecule, you take, and then it is okay, fine. You can run up to 30 picoseconds something. But and now the beauty is that even if you report 10 picoseconds, the people accept your answer. They are good with that. Yeah. So basically, since there is no ambiguity in anything, there is no question of parameterization of the force rate, because everything is maybe an issue. Even if you report 10 picoseconds also, you are definitely if you want to go for higher, especially I think a lemon will run up to 50 or 50 picoseconds. So lemon has published now. We kept right. We have taken 64 watt of molecule. But if you send an article of 50 picosecond classical MD, immediately we have to do I think send back. Is that?
even we have the NSM facility. Yes. Those nearby institutes can avail of that. That's the supercomputer mission. We have our computer here, the IT one. When you got that access from that, you can contact the computer center. Guide how to access it. But I don't think there is much fees. It is free, right? For the operation, after 3 months, it's so that they have to pay for certain CPU hours. It's very less, very little.
Charge,
That's not charged for CPU hours. But yeah, you can have this. Because there are other parts of the country also. Lot of this facility, NSL facility. There you can do. Okay.
So another thing is that I think by next 3 years, it is not DAP, it is India government. They are saying on XSL. You know XSL means? Can you tell XSL facility? You just add another into the 3 to 5. 1000 peta you have to want. 1000 peta you want. So you will see. So India will be in the big league. Once we because already USA having a one or two extra they have got. China also have got 2. So I think next 3 years we are going to get one extra. It is coming in another. So you can take a challenge to do CPMD or here. Okay. Nice.
Thank you very much.
Thank-
Yeah, so. Just a reminder to fill up your form.
So if you are facing any kind of problem during filling the form, you can approach us.
Lunch. So you meet at
Yeah, this is all whatever my PPT is there. I make it PDF. Okay.
Okay.